Hello everyone, my name is Zifan Wang. This video introduces our work in CVPR 2023. This is a joint collaboration with Nan, Tomer, Xi, and Radu from Google. In this work, we tackle the problem that deep networks are often vulnerable to human imperceptible noise from a learning theory perspective, that is PAC-Bayesian. Our results include a set of analyses that guide us to minimize the trace of hashing of the robust loss with respect to the network's weights during training. The goal is to make the model more robust at the test time. We therefore provide a new trace of hashing regularization term, and using this term, we're able to improve the state-of-art test robust accuracy with region transformers. If you found this work interesting, please feel free to join us in our poster session on Wednesday and with Nan. And here is our poster attack. The background of this work is as follows. We know that deep models are often vulnerable to small perturbations that is unlikely to humans. For example, recognizing a cat as a sports car, although they are nothing alike. When people are trying to fix this problem, we often just directly add in adversarial data during the training. But recent work has discovered the fact that if you do so, the model is very easy to overfeed to the adversarial data during training, and is not robust at all during test time. So formally, we observe a pretty large robust generalization gap on adversarial data, and is much bigger than the standard generalization gap on the benign data. So the contribution of this work is as follows. Our approach to study this generalization gap is by using PAC-Bayesian theory, which upper bounds the test loss by distributions of networks weights. In particular, in this work, we use PAC-Bayesian theory to upper bound the robust test loss and derive a minimized bound, which is tight and is useful to provide gradients during training. In particular, our bounds involve the trace of hashing term, and we show that regularizing this trace of hashing term for the top layer only empirically leads to a minimization of the trace of hashing for internal layers as well. Restricting this regularization on the top layer successfully scales up our algorithm to more than deep networks like vision transformers. As a result, we improve the robust accuracy on vision transformers by experimenting on standard vision dataset, CVPR10, CVPR100, and ImageNet. And we provide new state-of-art robust accuracy on this dataset. I'm going to briefly talk about our analytical result about PAC-Bayesian bound and how we conclude that we need to regularize it during training for robustness. We begin by introducing the conventional assumption about PAC-Bayesian theories. That is, we assume the network's parameter follow a zero mean spherical Gaussian with an unknown standard deviation, sigma z, before training. We call this prior distribution P. The corresponding posterior distribution of each parameter will assume to be Gaussian as well. So overall, we can see that the parameter vector theta after training follows a product of univariate Gaussian with mean of mu and the covariance matrix sigma. We call this posterior distribution Q. Notice that the mean and the covariance matrix of Q, they are optimizable, while the standard deviation of the prior distribution P stays unknown to us. Now I'm ready to introduce this so-called PAC-Bayesian bound. It says like with a probability 1 minus tau, the following equality holds. On the left-hand side is the test loss, is the expectation of the test loss, which is upper bound by the expectation of the training loss plus two additional terms. When I say expectation, I mean it's taking over the parameter distribution Q. And the two additional terms, the first one is the KL divergence between the posterior distribution P and the prior distribution P. Sorry, Q and P. And the last term is a constant, which is not a function of Q. So during optimization, well, it's okay to just ignore the constant Q, the constant C. So with this PAC-Bayesian equality, we put the term we care about, the robust test loss, on the left-hand side. And our goal is to minimize the right-hand side to make the bound as tight as possible, so we can find useful gradient during training to minimize the test loss. To do so, Our analytical result shows that minimizing the right-hand side with respect to Q is actually equivalent to set a network's parameter as the mean of Q, that is mu, and computer training loss, the squared L2 norm of mu, and an important term, which I highlight in red, the trace of Hessian matrix of the training loss with respect to the network's parameter mu for the moment. The additional term C and the higher order term can be just ignored during training. In short, this equation shows that for the purpose of generalization, we need to consider three components: the training loss, the squared L2 norm of the parameter, and the most important thing here, the trace of Hessian of the loss. So in geometry, the trace of Hessian is the sum of curvatures of the loss in all directions. So minimized trace of Hessian actually leads to a pretty flat minimum. But however, many of you have nightmare when facing with the computer required to calculate the trace of Hessian for any function, and it's obviously not feasible to compute it for more than deep neural networks. In this work, we provide examples showing that only regularizing the trace of Hessian for the top layer is effective to implicitly regularizing the trace of Hessian for internal layers as well. In the figure on the right, we plot the trace of Hessian for all layers when regularizing the top layer only, that is the orange curve, and when actually regularizing all of them, that is a green curve. We found two curves are pretty close to each other after some epochs. So it concludes that regularizing trace of Hessian for top layer only is enough empirically for decreasing the trace of Hessian for internal layers. Theorem 4 in our paper provides a way to study the internal activation to provide a way to explain why this regularization propagates to lower layers. Here is a brief overview of our results. The orange bars are the model trained with trace of Hessian plus traits, and it has much better robust accuracy measured under auto attack compared to the Bayesian method. If you found the results interesting, please stop by at our post section or check the paper for full results. And yes, please use this QR code to find our full paper and join us during our post session on Wednesday. Thanks for watching this video. I will see you at CVPR.